Hello, everyone, and thank you for joining us. My name is Janos Mathe, and I'm here with my colleague Tim Kaufman. Together, we'll be discussing the challenges and solutions of an interoperable clinical decision support implementation here at Vanderbilt University Medical Center. In the next 15 minutes, we'll walk you through the following main points. First, we will provide an overview of the Stratify project that served as the catalyst for this work. Second, we'll discuss the knowledge engineering approach we apply to Stratify. Then, we'll demonstrate our custom tool, the VUMC CQL platform. And finally, we'll close with a brief conclusion and open it up for discussions. Let's begin.
Stratify AHF presents a risk score to help in deciding whether a patient is at low risk for readmission due to heart failure. Providers are given the opportunity to view the risk score in the EHR when they're viewing the patient from the dashboard. Stratify AHF supports recalculating the risk score when the provider can enter certain missing data elements. At the provider's request, Stratify AHF recalculates the risk score based on new information. Stratify AHF operates by evaluating the embedded CQL definitions in the context of the selected patient. It displays all the relevant inputs that it can find in the EHR, shows the risk score, and puts it in context of general score distribution. Additionally, it highlights any missing data elements. Stratify AHF contains distinct calculation formulas that work when a subset of the data elements are unavailable, but sometimes there isn't enough data to calculate a score. Stratify AHF supports recalculating the risk score when the provider can enter certain missing data elements. At the provider's request, Stratify AHF recalculates the risk score based on new information.
We believe that by adhering to the FAIR principles, Stratify aligns very well with the MCBK initiative. Knowledge assets in Stratify are findable. We maintain formal knowledge bases to represent clinical concepts along with metadata, clinical terminologies, and EHR build references. Knowledge bases are stored in searchable text formats and navigable graph representations. They also are exported as FHIR value sets as part of the knowledge curation process. They are accessible. Knowledge assets are shared internally through institutional file sharing platforms and our CQL platform, and externally with CDS Connect and Value Set Authority Center according to the dissemination plan. They are interoperable. By leveraging clinical terminologies, FHIR value sets, and CQL, we ensure seamless integration with EHR systems that support these standards. And finally, they are reusable. Our implementation artifacts are openly shared in repositories and are adopted by external institutions like Oregon Health and Science University to advance the broader ecosystem of computable biomedical knowledge. Up until now, we've seen the Stratify tool in action, but how do we actually get from a proven research finding to a fully integrated CDS solution in the EHR? For this, we have to talk about knowledge engineering. The highlighted knowledge to practice section of the Learning Health System cycle from Flynn et al. Illustrates clinical research translating into actionable rules and workflows. In our case, we started with model generation encompassing steps 1 to 4, then moved to CDS implementation from tool design to the representation of logic, EHR integration, and measurement outcomes, ultimately enabling dissemination and maintenance. Although every stage benefits from knowledge engineering, our team's primary focus has been delivering real-time CDS, namely the user interface and the logic behind it. That's what we'll dive into now. So why do we need knowledge engineering? The main input we started with was a risk calculation formula from a research paper. Even though the math itself seemed straightforward, there were a lot of unspoken or undefined design considerations, like which measurement method or site is preferred for inputs like pulse ox and BMP. What do unnamed abstract concepts like prolonged QRS mean? Which units are used to store data? What are the valid data value ranges and data shelf life for each input? And how far to look back? How to handle missing data or select from multiple available values? All these details get clarified during the knowledge engineering process, ensuring that every new logic component builds on a clearly defined layer beneath. Using a detailed process, we created a coordinated set of standard-based CDS artifacts to implement the risk for calculation formula for Stratify. The artifacts include the clinical quality language implementation for fetching the data from the EHR as well as the calculation of the risk score. The clinical concepts providing the input data for the logic are identified with the help of standard-based medical terminologies including LOINC, RX norm, and ICD-10, and are packaged as FHIR value sets. The clinical concepts necessary for the implementation were identified by clinical terminology experts. They were cross-referenced with the EHR build components to make sure that we had the ability to identify the right data in our clinical systems. Finally, we performed a validation of the patient data associated with these concepts by comparing data obtained from our data warehouse with data pulled using the EHR FHIR interface. All of the concepts we used were captured through a domain-specific language, allowing us to record the relevant data and design decisions as a coordinated set of knowledge assets, forming our knowledge base. We then leveraged low-cost tools like version-controlled repositories, custom text and CQL editors, and model translator scripts to gather and refine this content and ultimately translate it into FHIR and CQL artifacts. Our knowledge base incorporates everything needed for clinical operations, from standardized terminology concepts and EHR build components to coding system identifiers, facilitated FHIR interfaces, and the logic definitions that underpin the various calculation formulas. Serving as the authoritative source for all operational artifacts, it let us automate much of the generation process, ensuring consistency across the board and streamlining ongoing maintenance, including changes to concepts, codes, and patient population specific coefficients. Here you can see two representation formats of the knowledge base, the textual specification and the knowledge graph.
Here in the Custom Product Development Group at VUMC, we are regularly asked to help build informatics solutions, particularly clinical decision support applications, that integrate with the EHR using FHIR. Stratify AHF is one of these projects. CQL Platform is a custom web application designed and implemented here at VUMC. It exists to help mainly with two tasks for Stratify AHF. First, identifying the appropriate concept codes for value sets that Stratify AHF requires, such as history of heart failure, diastolic blood pressure, and troponin lab results. Second, authoring the clinical quality language definitions that will request the needed data elements from the EHR and use them to calculate the Stratify AHF risk score. CQL Platform tries to lower the barriers to using FHIR to query the EHR directly and to evaluate CQL with the EHR as a data source. It aims to reduce the time and effort spent iterating through these activities. Several tasks are necessary to get started with retrieving data from an EHR by FHIR. CQL Platform tries to make these easier. It maintains a persistent list of known FHIR servers. These are configured once, regardless of informatics project, by a knowledgeable administrator. Each epic environment, such as proof of concept, TST, or production, has its own FHIR server address. To keep them organized, each is tagged with inherent properties such as the server's organization, like VUMC, whether it contains PHI, like prod or non-prod, and what FHIR version it supports, like R4 or DSTU2. Additionally, CQL Platform provides the ability to validate the presence of the servers and confirm their FHIR version. CQL Platform maintains a persistent project space for each individual project, such as Stratify AHF. Each EHR integration requires registering the application with the target EHR system so it can manage and authorize access. SQL Platform provides a persistent client registration record to store this information and reuse it as FHIR queries are requested later. Both data element mapping and CQL evaluation require having some data to look at, so CQL Platform supports persistent sample datasets, which specify FHIR queries for retrieving resources of interest, patients, encounters, observations, such as lab results and vital signs, etc. To help, CQL Platform checks the resources that the targeted FHIR server supports according to its published metadata, called the capability statement. Sample datasets can retrieve any type of resource, but the most common starting point is a patient resource. These will typically be resources for a patient in the EHR that is known to have characteristics relevant to the project. To get the desired patient, the FHIR ID could be used, but that is rarely available. More common is an MRN. The Epic FHIR API documentation says the identifier can be used with a specific format. In this case, the letters MRN and the MRN value separated by a type character. This MRN is known to identify a patient in the VMC test environment, so that query is tagged so that it only applies to that environment. This way, if CQL Platform is holding authentication tokens for more than one FHIR server, only the relevant ones will be queried. The very next thing is to find out the results of the query. This is available in the preview area, but retrieving data from the EHR requires authenticating. Here, CQL Platform offers the opportunity to authenticate using one of the client registrations for the project. The project is registered with the EHR, but final authority to access patient data lies with the provider who is asking for it. When authentication with the EHR is complete, the access token is held in the CQL Platform for as long as it lasts, typically 1 hour. Since CQL Platform holds valid authentication, it automatically retrieves the FHIR resources that were requested. It displays a table of all the values that are present in the patient resource so the correct patient can be confirmed visually. A sample dataset is a collection of multiple resources of the same type, so additional patient resources can be included. The preview automatically updates to retrieve all the new resources, and it displays data elements side by side for comparison, showing only elements where at least one of the resources has a value. Any type of FHIR resource may be important to a project, and many of them are closely related to a single central resource. Commonly, lab results and vital signs contained in observation resources are used, and these are related to patients by their subject field. CQL Platform supports adding a new sample dataset that is derived from another, in this case, observations derived from the existing set of patients. In this case, the EHR limits the FHIR queries for observations to just labs or vital signs, but not both. So adding the category field allows the query to be successful. Again, the preview automatically updates to retrieve all the new resources. The Stratify AHF project requires several inputs to its risk calculation formula, so identifying the appropriate codes to use for retrieving those inputs is a critical step. CQL Platform keeps a persistent set of data dictionaries where those codes can be explored, recorded, and applied to various sample datasets. To determine the appropriate codes for Stratify AHF to use when obtaining a patient's respiratory rate, for example, a data dictionary based on sample dataset of vital signs or labs can help. Knowledge sharing is a key feature of CQL Platform, so in this case there is already a data element mapping for respiratory rate available from another project. It uses one LOINC code to identify the relevant vital sign. The preview displays all the observations with matching codes. To determine the codes for Stratify AHF to use when obtaining a patient's blood oxygen level, creating a new data element mapping specifically for this project is an option. The standard code is not finding any matches within the dataset. CQL Platform supports reviewing the unfiltered resources from the sample datasets so that the matching resources can be identified and their codes directly added to the dictionary. With an additional code, the preview shows observations that match. Stratify AHF is implemented as a Smart-on-Fire application whose logic is written in CQL and evaluated with the CQL processing engine on demand when a provider asks to see the risk score. CQL Platform provides an environment to author and evaluate CQL. For example, based on the respiratory rate and blood oxygen level codes identified in the data dictionary, it's possible to write CQL that both retrieves the required data and performs calculations on it. CQL has functions for applying sophisticated data management, such as effective time windows and list filtering. The CQL can report all the relevant inputs and outputs that are needed for an application, including patient demographics. As the CQL is edited, the preview displays the results of evaluating it with the patients from the sample dataset as the target from the live EHR. Using the CQL platform to build the clinical logic in this way allows validation against real patients' data from the EHR, independent of efforts spent on building the custom application.
In conclusion, CQL and FHIR are instrumental and effective platforms for implementing interoperable CDS in modern EHRs. However, there are several key considerations. Implementing a tool with complexity comparable to our project demands substantial knowledge engineering effort to ensure clinical accuracy and maintainability of the logic. Establishing a production-ready solution also necessitates advanced technical expertise regarding the relevant standards like FHIR and CQL, general web app development, and EHR. Due to the incomplete implementation of the CQL specification by existing engines and inherent limitations within CQL itself, there are restrictions on both the expressivity and the brevity of the implemented CDS. These limitations may necessitate workarounds which would obscure the original logic. To address the lack of features for efficient CQL development and testing in available tools, we created dedicated software to bridge this gap. The resulting VUMC CQL platform has applications extending beyond the Stratify project and VUMC. Knowledge engineering played a very important role, which we have seen through the speed improvement we gained thanks to the decoupling of knowledge-based implementation from application development. When it comes to all stakeholders, precise and shared models, especially when supporting discussions, are a must for exposing and avoiding ambiguities in the implementation logic. Finally, we wanted to provide a summary of the challenges we encountered, many of which we covered today.